Hi, everyone, and welcome to today's webinar, Accurate De-Identification of Structured and Unstructured Medical Data at Scale. I'm Julia Moeller, and I'm joined here today by our speaker, Julio Bonis, data scientist at John Snow Labs. Before we get started, I'd like to cover a few housekeeping items. We welcome your questions today. If you have any questions, please type them into the GoToWebinar control panel on the side of your screen, and we'll be answering any questions at the end of the webinar. If you have any technical difficulties, please contact me and I'll try to help you out. My email is on the screen. And we will be sending out the recording for today's webinar, so you'll receive that in the next couple of days. Okay, at this time, I'd like to turn it over to you, Julio.
Thank you, Julia. We will talk about accurate identification of structured and unstructured medical data at the scale. My name is Julio Bonis, and I collaborate with John Snow Labs in the Spark NLP library. I would like to start with this history about what is known as Sweeney's demo attack. Dr. Sweeney is a computer scientist that works in Massachusetts, and she, at the end of the past century, she realized that only 6 voters had in Cambridge, Massachusetts, had the same date of birth than Governor Bill Weld. Only 3 were men, and only 1 lived in the same zip code that the governor at that time. And at the same time, there was a database freely available with medical records of people from Massachusetts. So she, by combining this information that was available from the voters registry with the information of this database, she was able to re-identify the medical records of the Governor Bill Weld, and in fact, she mailed the governor's office with the medical records. And this event changes dramatically how we approach the issue of privacy in healthcare data. Privacy is not only a question about the right to privacy, it's also a question about health, because when people feel that their data can be, their health information can be released to other ones, they start to develop some protective behaviors. And we have here one event that has happened 3 days ago about coronavirus, where one woman in India, in Agra, has hidden her condition to the doctors because she was probably afraid of releasing the condition and the consequences of that. So we need to keep in mind that ensuring privacy will also improve effective communication between physicians and patients, and that will increase the quality of care and even will protect public health. So it's important also because of that. We need to keep in mind also that personal health information is sensible not only for an employee or an insurer, but also for family members, because it can get you into some discrimination, stigma, or problems. And we need to also to keep in mind that privacy perceptions are different between people and cultures. And in fact, in US, 72% of population has reported to be worried about sharing personal information online. So this is a big problem. When you want to use health information for a secondary purpose, not only for direct healthcare, you have basically 2 options. You may think about asking patient for consent, or you may think in trying to anonymize. Asking patient for consent is not easy, because you can argue that when someone is asking for healthcare, they probably are not really free to give you consent. So at the end, everyone agree more or less that anonymizing this information is the way to go. Regarding the identification, we need to understand that this is not only a technological problem. All this thing about the identification starts with a good data governance and data policies. This is the base of everything. You can also apply some contractual approaches, signing contracts with people when you are sharing this information. And only at the end of this, when you have solved these two layers, then you can apply information technologies to help you to cope with this problem. In this webinar, we will focus in the technological solutions, technological approaches. And there are mainly two big different approaches for this problem. That is that are specified in the regulation in US, for example, in HIPAA. That is a big regulation about this issue in the United States. And basically, HIPAA differentiates between two different approaches. One is named expert determination, that is basically in statistical approaches. Basically, you will estimate risk of the identification. And then you have another approach that is called safe harbor, that is based in lists. And we will comment about these two approaches in this webinar. The first approach, we will start with the expert or risk-based approaches. When you are applying this approach, you always need to have to keep in mind that there will be always a balance between the identification risk and information loss. So in practice, it's impossible to reduce the risk of the data of re-identification to zero if you want to have something useful to do an analysis with. So you always have this balance between risk of re-identification and information loss. Information loss, you can measure it with different metrics like entropy, that is increased by generalization, and with missingness, that is the percentage of data points that are missing in the final identified data sets. And this missingness is increased by suppression. We will see this later on. And then you can also estimate the re-identification risk by using conditional probabilities. We will see this point now. We can differentiate two main categories of personal health information. You have this, what we call direct personal health information, that is things like your name, your social security number, your genome sequence, your face photography, your email, and those are elements that allows someone to identify you directly. In these cases, what you do is to mask these elements, and these elements will never be used in analysis, in further analysis. And then you have other kind of elements that are called indirect personal health information, that are those variables that by themselves cannot identify you directly, but when you combine them and you combine these elements with external sources, then it allows you to identify. Examples are dates, your date of birth, or dates of clinical events, zip codes, your profession, ethnicity, etc. For those cases, what you do is to de-identify those elements, so you can use those information in the analysis that you make after. You have basically three approaches or techniques for data identification. You can do generalization. For example, instead of putting the date of birth in the final dataset, you put the age, or you can truncate the zip code. You can do suppression. For example, for direct personal health information elements, you just remove those elements. You can remove all patient names. And even for indirect personal health information elements, sometimes you want to remove only outliers. For instance, just imagine a woman that have 9 children. You will probably want to remove that specific data for that specific woman, because this will allow someone to re-identify that record easily. And suppression basically will increase missingness, and generalization will increase entropy. And then you have the third approach or third technique, that is basically subsampling. You can take, instead of giving your whole population to a third party, you can just take a random sample. Basically, what you are doing here is increase the random missingness in the final data set. Regarding the threshold about at what level of risk are you able to cope with, or you believe is tolerable in cases? We have some data from past cold trials, and this is published in literature. Basically, the threshold goes between 5% and 33%. In the worst case scenario, when there are public, the data will be published and publicly available, and there's a high sensitive information and these kind of things, the threshold is put more or less in 5% applied to a single person in the database. And for cases where you are in a highly secure scenario with highly trusted recipients, third parties, and the information is not so sensible, then you can talk about 30%, more or less, 33%. This is the range of threshold. How can you estimate the risk of re-identification? This can be done by conditional probabilities, and you can differentiate 4 scenarios basically. The first one is when the recipient, the organization you are sharing data with, they try to re-identify this information, someone from the organization. And then you can basically estimate this risk by multiplying the probability of this recipient trying to re-identify by the probability of re-identifying in that case. Also, you have some cases where this re-identification happens just spontaneously. The recipient is not trying to re-identify, by chance someone from that organization finds a record that is from some relative of him. This can also be estimated knowing that the Dunbar number. The Dunbar number is a scientific grounded number that says the average number of people that someone will be related with, and this number is 150. So you can estimate that risk dividing this Dunbar number by the dataset size. You can also have another scenario where there's a data breach, and we know that 27% of HIPAA recipients will suffer a data breach at some point, so you can identify this. And also in the case of public data, you basically will consider, you will assume that in some point, someone will for sure with 100% probability will try to re-identify. So the risk is basically the probability of re-identification. But how can we estimate the probability of re-identification? There is one approach that is this is named key anonymity, and it's based in the concept of equivalence class. Equivalent class will be all the patients that share a common set of values for a group of personal health information. For example, you can say equivalence class is composed by all males born in 1977 with a diagnosis of diabetes living in Spain. So you can estimate the class size, the number of people that share these characteristics in your dataset, and then you can establish a minimum size for each of the equivalent class in your datasets. And you can say, if my minimum size is 100, then the maximum risk, the maximum probability of re-identification will be 1%. This is the way you estimate the probability, and you limit the probability of re-identification in this statistical approach. Then we have this list-based approach, or safe harbor. Safe harbor basically consists in a list of classes of types of personal health information that we agree, the regulator agree to remove from or anonymize from the original sources. And the regulator considered that if you remove all these 18 classes, types of personal health information, your source is, or to say, anonymized or anonymized enough. You can see here there's goes from names, geographic information, dates, telephone numbers, social security IDs. There's a lot of, and at the end they always add this last any other ID. So this list is really open to changes in technology or in kind of information we are dealing with. But when you are trying to apply this safe harbor in free text, in natural language, this is not so easy. You find some problems, practical problems. So for instance, you can have in a clinical note this source like printed by Johnson Sherry, and then you probably will be able to identify Johnson Sherry as a person name, and you can remove it, and this will be okay. This is a good way of anonymizing. But you can find sometimes the name of a doctor treating a patient. And doctor names, these names don't need to be identified at all. Or you can have this kidney stone surgery. A stone could be a surname. Some people is named a stone. So your system could be, if you apply a dictionary system, dictionary-based system, this stone will be removed, and this is wrong. Or you can have a patient with Parkinson, and Parkinson is a surname. Or you can have this Fergus Falls. And Fergus Falls could be someone that is named Fergus that has fallen, or could be the city Fergus Falls in Minnesota. So natural language is really difficult to cope with. And for natural language anonymization, we have basically 3 approaches. The first one is rule-based approach, where you develop some rules with regular expressions, for example, this kind of rules. It has some cons. Basically, it requires the domain expertise, and it's hard to cope with data drift. Data drift is when your data, you build a model based in rules that works very well, but the language evolves, and new terms and new ways of expressing things comes in your corpus. So your original rules start to be not enough, and maintaining this set of rules is very difficult. But it has some pros. It's easily explainable, and you can get basically quick wins with good performance when you have especially homogeneous corpus. And you can get these quick wins with a small set of, let's say, less than 100 rules. You can get good results at the beginning. Then you have this models-based approach, based on machine learning or deep learning. It has some cons. For instance, it requires a substantial initial effort in training. You need to annotate a lot of corpus to start to have some good results, and especially the problem is lack of explainability. And then you have some pros, of course. These models can capture contextual information much better than rules-based approaches, and are more generalizable to some extent. And mainly, you will get higher precision when comparing with rule-based approaches. And then you have the hybrid approach, where you combine rules with models. And probably the only cons is that it's more complex to deploy in practice. Although Spark NLP library can help you in dealing with this problem. And the pro is probably that you get a pragmatic balance between the rules and models approaches. When you have identified this personal health information, you can do 3 things basically. You can just remove it, as you see in the first example. You can tag, keeping some semantic information. So Williams you change by person, and Bristol you change by location. Or you can apply the more sophisticated one, that is obfuscation. That is basically you identify Williams as a name of a person, and instead of substituting by a tag, you substitute by a random name, Johnson. So you are anonymizing information by changing names or pieces of personal health information by other alternatives in a random way. How we evaluate our anonymization systems? We use basically the recall and precision metrics, and also the F-score metrics that are well described in the literature. I will not get into details on that. But just a note, in anonymization tasks, the recall is more important than precision most of the time. So sometimes you can use a weighted F-score where you give more weight to recall than to precision. And a very, very important thing to keep in mind here is that the evaluation unit must be the patient, not the token. In most cases, academics will use the token as the unit to evaluate. But in real scenarios, you want to evaluate how you anonymize the whole patient. If you are able to anonymize 99% of tokens of a given patient, but you fail to anonymize 100% of the direct personal health information tokens for that patient will be re-identified. So you have to keep this in mind also. And what are the thresholds in text anonymization? Basically, for direct personal health information, for recall is about 95%, for precision 80%, and for indirect personal health information, the recall is based in a formula you can see below that is based in these conditional probabilities. But more or less, you can establish 65% is much lower, and the precision is 70%. Some quick real-life tips in projects about anonymization. It's better to use methods that have been already used in the past. There are some new methods like differential error, synthetic data, or noise introduction that will not work, are more in an academic setting. Data custodians, you need to be sure that the data custodians want to automate anonymization. In some cases, some of the people that has this data, they don't have a problem anonymizing by hand, and they have to believe that automation is a good thing for them. And data users, the data scientists that will use that data, need to accept and understand these methods. Methods, of course, must comply with regulation. And you always need to keep in mind what is the use case, not only the data, but how this data will be used, because it puts some limitations in the way you can anonymize or not. And a very important thing, customized models at the end and customized rules are required in practice for most of the projects. You can start with a pre-trained system, but at the end, most of people at the end get to the conclusion that they need customized models. So just very, very briefly, I will go through John Snow Labs Spark NLP library that can help you to deal with this kind of projects. And this is a library that is based on Apache Spark. And the main advantage of this library is that it will allow you to scale. Once you have implemented a pipeline, you can scale in a lot of clusters, and for a huge amount of content is the best way to go, in my opinion. You have an open source edition that you can download directly and play with it. And then you have the healthcare edition that will give you an extra functionalities related with healthcare. And one of these functionalities is this data identification component that for I2B2 corpus is getting a state-of-the-art accuracy, 94%. We will see how can we build this pipeline. Basically, you have at the beginning of the pipeline, you will put the text, then you will do some pre-processing, you will get the tokens, then you will apply a deep learning name entity recognition model with some embeddings, word embeddings. So you identify entities, and then you apply a rule-based identification model, and finally you get the identification text. Very fast, very quick. You can import the library, it's very easy, and you can start the Spark session directly. It's very, very easy library to use. And let's say we have this source text here with a typical, with some personal health information pieces of data. So we will start the different components. We see here the document assemble, the sentence detector, and the tokenizer. And then we start the embeddings. We will use pre-trained embeddings, specifically trained for clinical content in English, and a name entity recognition model that is pre-trained also. We have this NER converter that will just identify the chunks of the entities. And then finally, you will start this the identification model that is pre-trained and is rule-based. So you compile the pipeline with this command in Python, and then you can fit and transform your data. And what you will get basically is from the original text, you identify the different entities. You can see it has identified the date, doctor, hospital, and street, and then the identification model will substitute those entities by tags. So you have this result that is anonymized. You can see how the dates will be changed. We will change the date December the 1st of 2016 by December the 7th, 2016. So this date is anonymized also. Or you can produce your own customized identification model with your own rules and your own dictionary of substitutions to obfuscation, and you can say to your custom model, I don't want to use the tagging approach. I want to use the obfuscation approach. So I want to change one name by another random name that I'm giving you in this text file. So we can compile our own custom pipeline, and then we will get the same. It's the same components, but at the end you can see as instead of putting a tag saying person or hospital, what you will get in this customized model is a chain in the name of the hospital by another hospital, and it is how it works. And this is the comparison between the two models, as you can see. And also there's in Spark NLP, there is a component that will allow you to also to identify structured information. Just imagine you have this table with personal health information. So you use this HIPAA class, and with the HIPAA class you feed with some elements, pre-annotated name entity recognition training corpus, a set of rules, and a set of we have seen set of elements for obfuscation, dictionaries for obfuscation. So with just 3 lines of code, you will get from your original table, you will get the final table where you can see that some columns has been replaced by a tag. Some columns like age or zip code has been obfuscated in the sense that when the age is over 90, like in the 3rd row, instead of 9080, you will get 90, or in the zip codes, you will get the obfuscated zip codes following the HIPAA guidelines. But for SBP and DBP, that stands for systolic blood pressure or diastolic blood pressure, as they are not personal health information at all, the component will keep those as the original one. So you can give this to the data scientists to make the analysis. I want to recommend these 2 books if you want to dig deeper in this issue. One is Anonymizing Health Data from Professor Khaled El-Eman, one of the best books. Some of this webinar is based on this book. And also you have this natural language processing with Spark NLP. This is a little bit outdated because it's based in 1.8 version. Now we are in 2.4, but it's a good starting point. And of course, going to the website and checking out the documentation and tutorials. So any question you have?
Yeah, so we have a couple of questions that came through. I know we're almost out of time, so as I go through a few questions here, feel free to continue to ask your questions, and we can follow up on anything after the webinar offline. I did also want to point out we will be sending over the recording, and I know a couple of people have also asked for a copy of the PowerPoint presentation, so we can send that over as well. And then for a couple of questions, so we got one, is it advisable to train your named entity resolution models in real implementations? And does Spark NLP allow to do that?
Yes, definitely. As I have said, you usually start with pre-trained models. If you are using Spark NLP, that we have some pre-trained models. But for most cases, especially if you want to share with third parties, at the end, most of the clients of projects I have worked with, they realize that they need to build their own models, and so they start to train their corpus and develop their own rules based in the specific use case. It's definitely is my recommendation.
Okay, and then what about customized obfuscation files with alternatives to names, cities? Should we apply different obfuscation files for each use case?
Yes, this is a good question, and definitely just you can imagine if you have a database in US, the names of people, names of hospitals and so on probably will be different than the database in China. So it's advisable to develop your own list of obfuscation replacement dictionaries. This is a very good idea.
Okay, and then last one, and we'll follow up on anything else after the webinar. How many documents are usually needed to get enough recall precision when training a custom model?
This is the $1 million question. Everyone wants to know that. I would say it's difficult to know in advance because will depend a lot on the nature of your content. But roughly estimation could be at least you will need to annotate 100 patients. It's the minimum number you will need to get some good results. And it's important to note here that depending on the kind of documents, you will need to add extra 100 patients. For instance, if you are identifying pathology records, it's not the same than identifying mental health records. So for each type of content, you will need to add 100, let's say 100 for a good starting point, 100 patients. Yeah.
All right, well, that's it for the questions for today. Anything else that comes up, feel free to shoot us an email and we'll get back to you. Other than that, that's it for today's webinar. Thank you, Julio. Thank you, everyone, for joining us today, and enjoy the rest of your day.
Thank you. See you.